Hi, my name is Javier Talavante, and here I will present this work titled Multi-Cell Deployment for Experimental Research in Visible Light Communication-Based Internet of Things. I carried out this work along with Borja Genoves Guzmán and Domenico Justiniano at Indea Networks Institute and Universidad Carlos III in Madrid, Spain. So LED market share in indoor illumination is increasing since it is superior to its competitors in terms of power efficiency and lifetime. Therefore, we can expect uniform indoor LED deployments aimed for illumination. Visible light communication can benefit from this since uniform LED lighting will enable dense Wi-Fi networks. But these kind of networks haven't been deeply studied to provide sufficient illumination simultaneously. VLC networks should aim to work as illumination deployments too, in order to provide effective IoT services indoors. This lack of joining between communication and illumination involves a lack of a proper dense VLC network testbed, and this slows down research since several experiments require dense VLC networks to be performed. And with these testbeds, also ad hoc setups can be avoided for these experiments. VLC provides illumination and communication simultaneously, so both things must be really fulfilled, and illumination must be sufficient and comfortable, compliant with illumination standards. The illumination properties of VLC transmitters and required backhaul connections must be studied in order to use them at the same times as VLC access points and efficient luminaries. We present here our multi-cell VLC setup compliant with illumination standards. We use off-the-shelf devices to help other researchers to deploy their own network and provide guidelines on how to build a network this kind. As a VLC access point, we use OpenVLC, which is a low-cost research-oriented platform. It uses a BeagleBone Black, which is a powerful and flexible single-board computer, and an OpenVLC cape, which contains the LED and enables VLC transmission. It can provide up to 400 kilobit per second in UDP throughput, which is sufficient for most of the IoT scenarios. We must know the illumination capabilities of the LED to find if it will be an appropriate luminary in our communication and illumination system. We assume the LED radiation to follow a Lambertian model, which is represented by this equation. And from the LED, we must know at least two important parameters, which are the Lambertian index M and the output luminous flux vis-a-vis, which is directly related to the total emitted lighting power, and it's measured in lumens. Here we can see how these two parameters affect the radiation pattern. Higher value on M will involve a more directional pattern, and higher vis-a-vis involve more emitted power and therefore greater illumination levels. These two parameters can be obtained by performing measurements on the illuminance provided by the LED along the right direction and assuming axial symmetry on the LED emission. With this experimental data, we fit by least squares the Lambertian model equation to this illuminance data. And from here, we obtained the M and Fis.V values. We perform this characterization for two OpenVLC versions. OpenVLC 1.3 is the latest open source version of OpenVLC, and a high power OpenVLC was characterized here, which uses the same LED and collimating lens, but drives more current to the LED, and therefore the emitted power is higher. In this table here, we can see the value of these two parameters for both OpenVLC capes. Notice how the Lambertian index is almost the same in both capes, since the LED and the collimating lens used are the same, but there is a substantial increase of flux in case of the high power OpenVLC with respect to OpenVLC 1.3. Knowing these parameters, we can proceed to analyze the provided illumination. We must comply with the illumination standards in terms of average luminance and uniformity, which is the ratio between average illuminance and maximum illuminance in the room. We considered a 7x5 transmitter grid in a room with these dimensions. And with this data, we can simulate the illuminance all across the room. And this is what we did in these two images. We simulated the illuminance in the room for both OpenVLC versions. We can see how the illuminance distribution is very similar in both cases, but we achieve higher illuminance levels by using the high power OpenVLC. We must comply with these illumination requirements, which are a greater average illuminance value than 500 lux, and the uniformity must be greater than 0.7. These are the typical required values to carry out tasks in a regular office. As we can see, both capes achieve the uniformity requirement since they use the same LED, but only the high power OpenVLC achieves the average luminance requirement. Therefore, OpenVLC 1.3 can't be used to provide uniform illumination in the room. For the network design, we used power over Ethernet to power and control the VLC access points. Power over Ethernet is a way to provide power through RJ45 cables, which are used in Ethernet networks. And we do this by using a PoE switch, which works as a regular switch and also can provide a PoE signal on its Ethernet ports. And the connection will work as shown in this image, where each VLC access point takes one Ethernet port, and also a laptop is connected to control this access point. Since neither the BeagleBone Black or OpenVLC Cape are prepared to use PoE signal, we use a PoE splitter to split the PoE signal into regular Ethernet signal and power signal. The power signal is down converted to 5 volt and split it to BeagleBone Black and OpenVLC. And the Ethernet signal is just bypassed to the BeagleBone Black Ethernet port, therefore enabling communication with BeagleBone Black. For the implementation, we programmed a graphic user interface. And here in this image, we can see the real connections, where the laptop takes one Ethernet port from the PoE switch, and a single VLC access point takes another Ethernet port, and using a PoE splitter in the middle. In the the graphic user interface, we can see how we can turn on and off individually each VLC access point. And also we can access to each of them via SSH, granting full access to the BeagleBone Black capabilities, and of course, enabling VLC transmission. We evaluated this network, different aspects of this network. First, the delay using a VLC receiver, using OpenVLC 1.3, also as a receiver. We measured the delay in this network from the laptop to this receiver, including the VLC link, and we achieved a value of 2.68 milliseconds. Also, we can monitor the power consumption from the PoE switch, and in this plot, we can see the power consumption at different stages of the VLC transmitter. When the BeagleBone Black is booting, there is an increase in power consumption. Then it decreases when it reaches an idle state. When we turn the LED on, we see another increase and a smaller increase when we start transmitting. And when we are finished, we can just power off the device, consuming no power and therefore saving the most energy possible. Also, about dense VLC networks, it's convenient to evaluate the cell area since we want to achieve full room VLC coverage. Here we evaluated this cell area from a distance of 1.5 meters to the LED, and we see how up to 0.65 meters away from the center of the VLC cell, we can achieve a maximum, almost the maximum UDP throughput received. So, given the setup we presented, this would mean overlapping cells, but this is expected when we try to achieve uniform illumination. But at the same time, this means that we can use cooperative schemes in this network. To conclude, we presented here our design choices for a Li-Fi multi-cell network and its implementation and evaluation. Particularly, we characterized and evaluated OpenVLC, both as VLC access point and as a luminary. We show how Power over Ethernet is a power and control alternative for this system, and how the whole network can be managed with a graphic user interface. Therefore, we have given the guidelines for additional multi-cell VLC deployments, and we expect to lay the foundations for further experiments in Li-Fi IoT, especially to those related to some of the most interesting aspects in VLC, which require a dense network, such as interference mitigation, cooperative techniques, or MIMO techniques. Thanks for your attention.